Really the idea again of electrons sort of transferring from one energy level to the next. And again, as they sort of do that, as we talked about, they essentially will release energy in the form of a photon of light, which is basically how energy is transferred. And we had some wave type of conversations here. We have our wavelength between our peaks. We also have our frequency, which is again how often a wave passes a particular point in a second. And we also have the speed of light there and an equation of c is equal to the wavelength times the frequency. And again, that is our speed of light, which is our constant. And 2.9979, I think, times 10 to the 8 meters per second. And we have our wavelength, which does need to be in meters, and our frequency, which is in reciprocal seconds, any one of these sort of units. Also, a hertz is basically a one-to-one relationship between a reciprocal second, and that's also sometimes what is used there. So we could use this, just rearranging this equation, and if we know the wavelength, we get the frequency, and if we know the frequency, we could get the wavelength from that there. And we talked about sort of the electromagnetic spectrum. And again, not all transitions will result in sort of energy coming off in the visible part of the spectrum. They may come off in other parts. And we have things like radio waves, microwaves, infrared, the visible part of the spectrum where we do see colors. We have UV. We also have some X-rays and gamma rays. Remember the relationship sort of between a wave and energy is the kind of smaller the wavelength. Thank you. Kind of smaller the wavelength, the higher the frequency. And also that usually is higher in energy, as opposed to, again, something with a much sort of longer wavelength. So when we have a longer wavelength, we usually have a lower frequency, and that usually is lower in energy. Any questions on any of that there that we were talking about? All right. So atoms and molecules can emit, as we talked about, this idea of sort of this quantized energy. And remember that when we talk about sort of quantized energy, we're talking about really sort of the idea that in the case, for example, of electrons, they will either gain or lose enough energy to sort of fully transition from one energy level to the next. As we sort of talked about, they won't really ever find themselves sort of between energy levels. So I think we talked about sort of like a staircase sort of example. You know, you're usually on a step, on one step or the other. You never, again, usually sort of stop halfway between the steps. And again, that's sort of how electrons sort of transition from energy levels. They gain or lose enough energy to fully make those transitions. And again, those transitions may be one energy level, they may be a couple of energy levels, but they're able to sort of really make that transition. We could actually calculate the energy associated with that photon of light or needed to make those transitions by using this equation. E is energy and is in joules, times h, which is a constant, so another number there that you need to know, which is Planck's constant, and that is 6.63 times 10 to the minus 34. Again, that is joules times seconds is the units there, so joules times seconds. Again, joules being energy, seconds being time. And here we have our frequency, which is in reciprocal times. Reciprocal seconds. So we have reciprocal seconds, we have joules times seconds. So when you multiply those together, we do end up with basically joules left over in terms of the units when it's all said and done. Now this equation here can also be used with the previous equation that we saw there, and that was our c is equal to our wavelength times our frequency. And in this particular case, if we solve for the frequency, it is c divided by the wavelength, which means if we take that, we could actually substitute it into this equation, and that will give us E is equal to hc divided by the wavelength. Now, in this particular case, both of these are constants. which means that essentially if you know the wavelength, you could also calculate the energy associated with that photon of light. And obviously here from the original equation, if you know the frequency, you could also calculate the energy associated with it. So you really just need to know one of those two things, the energy, to calculate the energy, the frequency, or the wavelength. Any questions on that there? Yeah.
So you're saying that those two formulas kind of interchangeable for finding the energy?
Yeah, so there are multiple ways you could do it. So for example, if you have the frequency, you could go right into, the E equals H times the frequency. If you have the wavelength, you could go into the one with the HC over the wavelength. If you have the wavelength, you could still, by the way, you could still do this equation first and get the frequency and then put it in there in kind of a two-step process. If you want, you'll get the same answer and stuff like that. Here again, though, the wavelength does need to be in meters so that it, again, still properly cancels out with the speed of light, which is in meters as well. So you want to make sure that they are in the correct units. Again, very common units of wavelength are meters and nanometers, especially with visible part of the spectrum where we see the colors, the red, orange, yellow, green, blue, indigo, and violet. Those are oftentimes given in nanometers. So that nano conversion to meters is used a lot when you're kind of doing these calculations. I would definitely say. Other questions? All right, so why don't you take a second, speaking of that there, and what is the energy associated with a wave that has a wavelength of 465 nanometers? So take a moment there, see what you come up with. We're looking for energy, which again gives us our equation. We do have the wavelength given to us. So once again here, we can't really go directly per se into here without sort of substituting in that other equation, which gives us basically this version here of it. And again, we're substituting in from here, c divided by the wavelength from our first equation. And these are both constants. So again, Planck's constant 6.63 times 10 to the minus 34 joules times seconds. C is the speed of light, 2.9979 times 10 to the 8 meters per second. And that's pretty much all we need. We do need to, again, make sure that our units are correct, and that is nano. And again, nano being 10 to the minus 9. So that means in 1 nanometer, there are 10 to the minus 9 meters. So that would get us 495 nanometers. On the bottom here would go our nanometers. And up on top, 10 to the minus 9 meters. That would get up here 495 times. Gonna get it in the right units to work with our speed of light. And that gives us E is equal to 6.63 times 10 to the minus 34 joule times seconds times our speed of light. Too many numbers times 10 to the 8 meters per second. All divided by our wavelength has been converted into meters, and that will allow that to cancel out correctly. The seconds will cancel out. Once again, just going to leave you joules. Yeah. It is supposed to be 465. It is. Thank you very much. It's like 95, but just so wrong. All right. So thank you. So 465 there. There we go. Thank you. There we go. So it'd be 465 times 10 to the. And that's going to get us something like 4.27 times 10 to the minus 19 joules in this case here. On the calculation. Probably helps use the right number as well. Would probably help with my calculation. Any questions on that? Okay. Let's try another one here. What is the energy in joules with a wave that has a frequency of 2.87 times 10 to the 14 reciprocal seconds? Okay, so on this one, again, we're looking for the energy, and in this case, we are given the frequency. So that means we actually are good to go. We could just go right into here. Once again, you should always think of you have Planck's constant available to you. Planck's constant and also obviously the speed of light are usually never mentioned in any problem, so they're just kind of values that they just assume that you know. And since at this school they want you to know it, you should know it as well. So in this case, we just go in and we got 6.63 times 10 to the minus 34. Joules times seconds times our frequency of 2.87 times 10 to the 14 reciprocal seconds. Here, the seconds will actually cancel. Once again, going to leave us joules, and that would get us here. Looks like 1.90 times 10 to the minus 19 joules. Any questions on that one? So again, that equation there, along with obviously this one that we saw earlier, those are two that are very commonly used and also very commonly used together to do problems. Any questions on any of those calculations there? All right, so again, what we've been talking about is really the end result of sort of electrons as they're transitioning. As we talked about, because waves and photons of light do carry different energies associated with it, even when we do see different colors, we can make an estimate in terms of maybe how far an electron is dropping versus when we see a different color. So remember, red sort of the longer wavelengths, kind of lower in energy. So again, a transition of electron from not too many energy levels may give off obviously a photon of light in the red part of the visible spectrum. Now, Bohr's theory of the hydrogen model, as we'll talk about, or the hydrogen atom, again, is a theory and not so correct in all aspects of it. We'll talk a little bit about it as we continue. But as these electrons are sort of transitioning, giving off energy, and also a reminder in terms of energy, if we are looking at an electron going upwards in energy, again, that's going to be an endothermic process for the atom. It has to gain some energy to allow the electrons really to go up. And you put it into the flame, the atoms gained all that energy, obviously, from the flame, excited those electrons to a higher energy state. And that's opposite when our electron, again, starts at a higher energy level and kind of works its way back down, which is essentially what it wants to do. As we've talked about, again, things in chemistry, really the whole purpose of a lot of things that happen in chemistry is to lower the overall energy of everything. So things in high states of energy are not really stable and they really don't want to be there. So that when they do get excited up, will try to work their way back down to a lower state of energy. And for the atom itself, that's going to be an exothermic process because those electrons transition down from a higher energy to a low, release that energy. And when it does so, it sometimes will give off what are referred to as an emission spectrum. Emission is usually what happens as the electrons are dropping down in energy and the atoms releasing that energy. And there's a couple of different types of emission spectrums that we'll talk about, but you could do that just like I just talked about, like in a flame test when you stick it into a flame. You could also do it with electricity, electrical discharge sort of tubes, lamps basically, kind of like neon lights. You pop on, run some electrical currents through it. It's going to excite all the electrons in there, and you get all the pretty different colors from like neon lights. Now, the red hot, for example, when we see an iron bar at a high temperature glows, again, is the visible part of the spectrum. The warmth that we feel does come from the infrared. So as I've been talking about, not all addition of electrons, for example, will give off colors. So they can give off wavelengths that fall anywhere on that emission spectrum that we talked about, where we saw the radio waves, infrared, the UV, and all type of things. Now, a common sort of feature of emission spectrums of the sun and when solids are heated is it gives a more continuous spectrum. And a continuous spectrum is pretty much what it sounds like. The wavelengths of pretty much all light is represented. So that is very different than sort of the idea of sort of quantized energy. So when we have more of a continuous spectrum, and we'll kind of see a picture of this a little bit here in a second, but you could think of it not so much like a staircase, but more like you're walking up like a ramp. And if you were walking up a ramp, you pretty much could just stop anywhere along the way, right? If you're just kind of walking up a ramp, no stairs, you could pretty much lay up anywhere you want. And that's sort of what we see with the continuous spectrum. You pretty much see like everything coming out. So for example, if you looked at something that was lit by, for example, natural light, the sun, you see kind of almost like a rainbow. If you're looking at colors through a prism, you see like them all basically happening at once, like a whole rainbow. Everything's coming off basically at once. And that is different than when we look at atoms in the gas phase. And atoms in the gas phase, they actually don't show this continuous spectrum. They do show what is sometimes referred to as a line spectrum. And a line spectrum is pretty much what it sounds like. If you look at it through like a prism, a spectroscope that has a prism in it, what you will actually see is very distinct lines coming out at different wavelengths with different colors. And every element actually has its unique line spectrum. So you could look at a spectrum for a particular element if you weren't sure what it was, based on the colors of the lines that you see, based on the wavelengths that they come out at, will be very specific for individual elements. And that's a common experiment sometimes people do is they look at some known lights and then you get like an unknown light. And based on, again, the lines that you see, you can actually kind of determine what element you're doing. So, and that's happened because what we see here is actually electrons transitioning energy levels in a quantized fashion. Again, like our staircase sort of idea, they're either on one energy level or the next. And what that does is gives you, kind of a nice clean line of energy that is being transitioned. Each of those sort of lines would represent, for example, electrons transitioning from one energy level to the next. And that's sort of what it looks like if you look at something through a prism, and it will spread it out in terms of the different colors. This is again more of a continuous spectrum up here, where we do see pretty much everybody coming out at once, as opposed to what we see here and what we see with atoms of elements in the gas phases is more line sort of spectrum that comes out. Again, each of those lines have specific wavelengths corresponding to electrons transitioning from different energy levels. And that's more of our quantized energy. Here's that. I think it'll play. Maybe.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
So again, that more kind of line spectrum. And Bohr basically used his theory of the hydrogen atom to explain why we see these 4 sort of lines. And again, he reasoned that each of these lines again represents a electron transitioning from, again, one energy level to the next. As we talked about previously, that is more red, which would be perhaps a smaller transition of energy for that electron, versus this side, which is again more of the purple violet, which may have resulted from an electron transitioning a good amount of sort of energy. Again, remember that the energy, the higher the energy, the lower the wavelength or the shorter the wavelength. So an electron transitioning multiple energy levels, it could get off a lot higher amount of energy, and that would correspond to a wave that has a shorter wavelength, versus again, electron on the right there, maybe just transitioning one energy level, going to give off a smaller amount of energy corresponding to a longer wavelength of light that's going to come off. And that's again what we kind of see here. So Bohr basically reasoned or explained the emission spectrum that we see with hydrogen as basically these electrons transitioning. Obviously, we're not going to go into great detail about it, but it is basically sort of the planetary model, if you will. His idea was you have your nucleus, where you have your protons, obviously, and you have these nice little pretty orbits. And within these orbits, the electrons would be kind of circling around the nucleus. And what we're seeing here again is an electron jumping from this energy level, for example, to this one, or maybe an electron out here jumping downward. And the atom releasing that energy that accounts for those lines that we see in the line spectrum. And what he basically said was, again, an electron would be housed in one of these orbits. And as we'll talk about, that's not so true, and it doesn't really hold up, by the way, Bohr's model. As you go sort of past hydrogen, it has more than one electron. And the idea here of electrons essentially in these orbits kind of circling, where you could kind of put your finger on it and we'll just wait for it to kind of come back around. As we'll talk about, really not so true or holds up as they continue on. Now, when we look at this, each of these guys have a different energy level. And this is what is sometimes referred to as, for example, n is equal to 1. This is like n is equal to 2. N is equal to 3. N is the principal quantum number. It is basically the energy level. And as you can see there, n equals 1 is basically closer to the nucleus. And n equals 2, 3, and so forth are further away from the nucleus. And again, what we're looking at here is those transition of electrons from one energy level to the next, giving off that photon of light, the atom, as a result of it, those transitions that occur. Now, as I mentioned before, n is the principal quantum number, and that is basically a fancy way of saying energy level. N actually could have values of 1 through 7, so there's kind of like 7 energy levels if you want to think about it within an atom. And n equals 1 is the ground state. That is the lowest in energy. That's the closest to the nucleus. That is the most stable sort of orbit. So again, the idea of things being in lowest energy levels are the stable sort of situation. And again, anything above that, kind of like n from 2 to 7, those are what are referred to as excited states. So those are higher in energy. They are further away from basically the nucleus of the atom. So as the value of n increases, so does sort of the distance from the nucleus as well. And electrons, again, are thought to obviously be housed on these different energy levels. Ideally, as we will talk about, the most stable sort of arrangement is to get your electrons in sort of the lowest states of energy that's possible. And again, here, as I was just talking about, this sort of transition of just one energy level, a little longer of a wavelength, more like red, as this guy obviously is transferring a larger amount of energy going to be given off. And here we see something more like a blue color, which has a shorter wavelength associated with it. So in sort of Bohr's model, this was his idea. Each of those colors that we see is a result of electrons transitioning at different different energy levels. And for sort of main transitions happening in sort of hydrogen atoms that are occurring. And again, on the left here is sort of that idea of quantized energy versus sort of continuous energy. And as you can see here, unlike in a continuous sort of energy like we talk about with the sun and so forth, pretty much you can have energy stopping anywhere along the way, which would mean, again, electrons could essentially stop anywhere along the way, which is why you see all the wavelengths of light basically coming off at once. Here, our electrons are kind of restricted to, they gotta be either, here or here. They cannot just find themselves, between energy levels or anything like that. So again, they're going to gain enough energy to make those transitions fully. And by the way, you calculate that energy just like we did previously by using that equation right there, or maybe, this version of that equation. Again, that will account for the energy that's going to happen as that photon of light gets released. And here's a prettier picture than my stereo pictures, but again, the guy on the left there, more of a ramp where, as we were talking about, if you were just walking up this thing, you could stop anywhere along the way. Here in a staircase model, you got to be on the different stairs, again, related to the different energy levels where you got to find electrons basically housed. So, as I mentioned before, Bohr's model of the atom, sort of planetary model of the atom, worked really well with hydrogen, which only has one electron. But once you start introducing a lot more electrons into play, it didn't really hold up over the long period of time. Again, a theory or model, right, is something that may be correct or may be found later on that may not be sort of correct. So idea of Bohr, and to this other idea of sort of how electrons are in the atom. So why Bohr's atom was electrons were restricted to orbiting those orbits around the nucleus. A lot of times for decades, no one could sort of understand the idea of, how they're able to kind of do that for fixed distance. They actually came up with one of the first ideas that sort of moved us away from Bohr's idea of the orbiting sort of electrons in these orbits. And he thought of the idea that if can behave like a stream of particles, then particles also could possess sort of wave-like function. So according to de Broglie, he thought an electron was bound to the nucleus wave, kind of like a guitar string, right? If you pluck a guitar string, it's attached to the guitar, right? So the wave won't fly away off the guitar string doesn't fly off of the guitar. It will still have wave-like functions. If you pluck it, it will look like a wave, but it's a standing wave because it's basically fixed down by the 2 points, right? That's attached to the guitar. And that's sort of the idea there of electrons. As we talked about, the nucleus, right, has an overall positive charge because of the protons that are present. And we have these electrons out there which are essentially tied to the nucleus by that electrostatic attraction, right? So kind of like your guitar string is attached to the guitar, the electrons again have sort of an attachment to the nucleus, which kind of keeps it there, but it can still travel like a wave and have wave-like functions. Yeah. Yeah. Any electron, any particle like an electron can act like a standing wave. Again, it's going to feel some attraction to the nucleus, which basically keeps it, if you want to think about it this way, it kind of keeps it in the atom, if you will, without sort of something to kind of attach it, right? It could just kind of fly off at will, if you will. So there is something sort of keeping it there. And as we'll talk about, depending on the position and the energy level of those electrons, that sort of attraction, or if you want to think about string, is like tighter than maybe an electron further out, which is not held as tightly as well, but still feels some type of attraction to the nucleus. So even those electrons further out in the highest energy levels will still feel that attractive force to the nucleus. And that's again what sort of keeps it there. Yeah. Other questions? Yeah.
The electrons go around the nucleus. So what that just stated is although it goes around the nucleus, it still behaves like a wavelength that goes like directly out.
Yeah, so the idea here is we're actually moving away from the idea of Bohr. So in Bohr's model, his idea was electrons are in these pretty little orbit circles and they're circling around in circles, and they actually don't travel that way. And that was sort of the early idea that they're kind of restricted to just those orbits kind of traveling in these pretty little circles around the nucleus. And the idea of what came after Bohr, which is what we're talking about here, starting with de Broglie and a couple other people, the idea is they really don't move in that sort of fashion, like a very predictable fashion of like it's strictly in this orbit and they're just going around in pretty circles and stuff like that. They don't. They move pretty randomly about the nucleus, and they move about with some wave-like characteristics, and they have this sort of attachment, if you will, point, like a guitar string, if you will, to the guitar, to the nucleus that doesn't allow them to sort of travel. But do they travel in these pretty circles? The answer, as we'll talk about in a few slides here, is actually no. They actually don't travel like Bohr. So that's why we're moving away from sort of Bohr's model to a new sort of model, this kind of wave mechanical model and stuff like that. So as I mentioned before, there are some points along the string which are referred to as nodes, and like a guitar string or something like that, that's basically a node when you think amplitude. Basically, the wave is kind of not up or down, it's just kind of flat there, and that's sort of a point where a node is. It basically has no amplitude. A reminder that and the height of the wave from the midline, and there's points in a wave-like time function which are known as nodes. Now, another really important idea that moves us away from sort of Bohr's model of these orbits is the idea that came about through Heisenberg's uncertainty principle. And the idea of Heisenberg's uncertainty principle is this idea that it's impossible to know simultaneously both the momentum and the position of a particle like an electron, for example. So essentially the idea of Heisenberg's uncertainty principle is this: the more that you know about one of those things, the more that you know about the position of a particle like an electron, the less you know about how it's traveling, and vice versa. The more you know about sort of how it's traveling, you know less and less about sort of where it's at that particular point in time. So what we're doing with this sort of wave mechanical idea is we're moving away from Bohr's model of, for sure, like, hey, I know electrons are in these orbits, they're circling, they're going around these orbits. Like, it's very predictable of exactly where I could find an electron sort of traveling around the nucleus, to this idea of, we really don't know at any given point in time exactly how the electron is traveling or its exact location. We do know that it's got to be sort of anchored down, if you will, towards the nucleus. There has to be some type of attraction near the nucleus which keeps it there. But where it's exactly at all given points in times, we really don't have exact knowledge of it, and that's very different than the orbit sort of idea, where you could just go, hey, it's in this orbit, and obviously it's going around in a circle. At some point, if you just wait for it, it should come back around, obviously, the circle, and it'll run into you. Now, this was another big sort of idea of moving away from Bohr's model to this new model, and sort of the last major sort of wave mechanical thing, which we definitely aren't going to get into too much of this. If you ever take physical chemistry, it's the whole first semester, I think. Bunch of calculus happening there. To this idea of electron density and sort of probability. And the idea here is, well, based on Heisenberg's idea, based on Schrodinger's equations, and based on de Broglie's idea, we really don't know how these electrons are moving. We really don't know at any given point in time exactly where we could find an electron exactly. The best that we could do is think about it in terms of probability, mathematical probability sort of determination. And the idea here is, well, there could be a very high probability of finding an electron in a particular point within the atom, but we still actually don't know, even if there's a high probability, we still don't know where it's exactly at or how it's moving or anything like that. So this idea of probability and electron density moves us away from Bohr's idea of orbits to this idea of orbitals, or atomic orbitals. And atomic orbitals are basically within the atom these probability maps of where you could find an electron. And as we'll talk about, there are a few different types of atomic orbitals. There are s orbitals, p orbitals, d orbitals, and f orbitals. And these are all the places within the atom of where we find electrons basically housed. They are, again, basically probability maps. And for example, as we'll see a picture, an s orbital, for example, is like a sphere. And if you think of the nucleus sort of in the middle-ish, the very high probability of finding an electron would be obviously in the area near the nucleus because of the electrostatic attraction between those things. As you would fan out from the nucleus, the probability would get sort of smaller. Doesn't mean way away from the nucleus you can never find an electron. The answer is no. There's just a lower probability. There's very good chance there could be an electron out there. But regardless of where you're at, even if you're like near the nucleus, if you're out here furthest away from the nucleus, you still don't know where it's at really at any given point in time. You still don't know how it's traveling. You don't know how it got there. You just know in these cases here, in terms of probability, that there's a really good chance if you're near the nucleus, there should be an electron there. Again, not sure how it's moving. It's not moving these pretty circles or anything like that, but there's a really good probability of finding an electron there. Yes, sir. As you can see here with this much better picture. Yeah.
Look, that and based on Heisenberg's uncertainty principle, you said that you can either know where it's, how fast it's moving,
Yeah.
or where it's at.
Yeah.
So basically saying that it is kind of possible to see like general location, but we won't know how fast it's moving then.
Yeah, so like the more if you kind of like, exactly. So for example, the more if you like, all right, well, this location looks pretty good probability wise of like it should be somewhere in that location. That means the less you know about how it's actually moving in that location and where, where exactly it is at that point, you can't just like sit here and wait for it to, for example, go around the corner and a turn or anything like that. It could be just traveling like randomly, all bouncing around in that empty space. And eventually, it might hit the point where you're at, right? But you can't really predict, to certainty of like it's going to be there. And that's very different than Bohr's model where he had those orbits. And well, the electron has to be in those orbits. So by process of elimination, if they're just going around in a circle, it's very predictable that, you're going to just wait it out and eventually be at that location, right? You could be here, and the idea is it may never actually hit that point, right? It may actually become near it, pass it, and stuff like that, but it may actually never hit that point perfectly and stuff like that, as opposed to it orbiting in an actual orbit where it's a 360 predictable sort of idea there, if you want to imagine it that way. Like eventually, if you just wait, it should come back around, the turn and stuff like that. Questions on that? Yeah. So there's a much better one there before I scribbled on it. But again, the darker area, this is actually a probability map, and this is the idea of orbitals. And again, sort of that darker color there of red is again a higher probability of finding an electron near that location. And you could kind of imagine the sense that the nucleus is sort of in the center, and all that kind of probability maps that empty space, right? That Rutherford was talking about, where electrons are basically traveling, sometimes called the electron cloud. And again, it's traveling pretty random about that sort of space. That's also why, again, even on the fringes, right? Because it's traveling randomly, you could get an electron that pops out there. And again, you don't know exactly when it'll be there or how it got there. And that's, again, the idea of more of this wave mechanical sort of model of how electrons are basically moving. So let's talk a little bit about these atomic orbitals, which again are these sort of probability maps of where we find electrons. The first type of atomic orbital is an s orbital. And s orbitals actually begin on the n equals 1 level. So remember, the n equals 1 level is the lowest energy level. It is the ground state. It is closest to the nucleus. And on the n equals 1 level, that is pretty much the only orbitals there are. So if you were to kind of look at the n equals 1, if this line represents an orbital, the only one you'll find on that energy level is what is referred to as a 1s orbital. You might be able to imagine the 1 in the 1s means it's on the first energy level. Is basically what that 1 means. The s means it's an s orbital. You will also find on every energy level s orbitals. So if you continue up your path of energy levels, there's an s orbital on every single energy level. In terms of s orbitals, there's only one type of s orbital. No matter what energy level you're at, there's basically only one type of s orbital. Now, by the way, any individual orbital that we talk about, no matter what it is, any individual orbital can hold a maximum of 2 electrons. So any individual orbital can basically hold a maximum of 2 electrons. So for example, this one here, if arrows are my electrons, can basically hold a maximum of 2 electrons. This guy here can only hold a maximum of 2 electrons, 2 electrons. So any individual orbital, be it an s orbital, p orbital, d orbital, an f orbital, just one single individual orbital could only hold a maximum of 2 electrons. It does not necessarily need to hold both electrons. It could actually hold one if you want, but maxed out, it could only hold a maximum of 2. So basically, if you want to max out an s orbital on any energy level, you could only put 2 electrons in there. Yeah. Say it again. A 1s orbital is a sphere. Is that what you're asking? Or
N equals 2 and you have 2s and then n equals
yeah, these are different energy levels. So remember, the n is the energy levels. So this is the ground state. This is technically the first energy level that's closest to the nucleus. This would be the second energy level, which is further away from the nucleus, higher in energy. This would be the third energy level. There's like, remember, N could go basically 7 different energy levels. And as you continue up in terms of N, the number gets higher. That is technically higher in energy and further away from the nucleus. So like these electrons here are further away from the nucleus than these guys here, which are much closer to the nucleus in this case.
Still have it as well.
Every single energy level has an s orbital. Yeah, you'll find an s orbital on every single one, 1 through 7. They all have s orbitals. The name just changes, and again, that's the number in front. That 2s means it's an s orbital on the second energy level. 3s means it's an s orbital on the third energy level. So that number in front is actually the principal quantum number, is basically the energy level. And that's how we identify, for example, we're talking about like the 1s orbital, which is on the first energy level, versus like the 3s orbital, which would be on the third. Yeah. It does, and we're going to talk about that as we go on. So we'll get to that, but it actually does matter which way you kind of put them in and stuff like that. Yeah. All right. So as I mentioned before, a 1s orbital is basically a sphere. It's basically that picture we just saw with the kind of pink basically smeared out there, and this right here. So
An s orbital has a spherical shape with the nucleus at the center.
So again, the nucleus is in the center, and we kind of think of these orbitals being on in like math, the x, y, and z sort of coordinate plane there in 3-dimensional space as to how they are basically laid out there. Now here again is our probability map, again, much darker in this area, as we found out, a lower probability of finding an electron, and that's essentially what an s orbital looks like. They're basically just spheres. They actually do get larger as you go from one energy level to the next to accommodate all the electrons that are there, right? So as you continue going upwards in energy, there's going to be a lot more electrons sort of present. Now, p orbitals actually begin on the second energy level. That is where they begin. So on the first energy level, we have S's only. When we get to the second energy level, that is actually when we start to see p orbitals first appear. And then you'll actually see p orbitals pretty much on every other energy level after that. So they don't start until the second energy level. So on that first energy level, we have our 1s orbital. On the second energy level, we have our 2s orbital. And this is where we actually start to see our p orbitals begin. There's actually 3 different types of p orbitals. So there's actually 3 different types. That is px, py, and a pz orbital. The x, y, and z is that coordinate plane we just saw there. Basically, is it an x, y, or z sort of orientation in 3-dimensional space? And because there's 3 of them, we would represent that, for example, with 3 little lines, each one representing a different p orbital, for example, px, py, and pz in this case. That means that if we were to fill up all of the p orbitals on an energy level, how many total electrons could we put in there? Yeah, we can max out at 6 electrons. Again, 1, 2, 3, 4, 5, and 6 electrons can basically go in there. Now, when we have a orbital like this, like p orbitals, and we'll actually see it with d orbitals and f orbitals as well. When you have multiple orbitals that make up sort of on a particular energy level, it is sometimes referred to, if you took all 3 of those together, this is sometimes referred to as a subshell or sublevel, depending on your book. And that is basically a grouping of the same type of orbitals on the same energy level. So individually, the px orbital, the py orbital, and the pz orbital, individually, they could only hold 2 electrons. But when you group all of those together on energy level, they're referred to as a subshell, and the 2p subshell could hold 6 electrons total when you take all the individual p orbitals together. We do not refer to s orbitals as a subshell because there's only one type of s orbital on any energy level. So it's just basically an orbital. So we don't usually use that word subshell or sublevel with s because there's only one orbital. But when you have orbitals that basically come as groups of individual orbitals together, that is what is referred to as a subshell or sublevel. That happens with p, d, and f, as we will see. And those are sometimes referred to as subshells. Any questions on that there? Here again is what a p orbital looks like, kind of like a figure eight is described as. You can see that is the px orbital. It's on the x-axis there, right?
The 2px orbital is in the shape of a figure eight along the x-axis.
So when you look in the middle, that is what's considered the node there, right? There's no amplitude in that sort of wave function. That's also in the middle there. I don't know if you kind of see it, but in the middle, that is where you kind of envision the nucleus sort of being, yeah? And you got these kind of two lobes of where electrons could be probably found. Again, not sure exactly where they're at in there, but again, higher probability towards the center where there's kind of no amplitude, where kind of the nucleus would be. Here's the 2py.
The 2py
Again.
orbital is in the shape of a figure eight along the y-axis.
And here is our z.
It's in the shape of a
Mentioned before, you could kind of think of the nucleus being in that part where there's kind of no amplitude. And you could kind of see here, the kind of darkish bluish color is near that point. Again, having probably the highest probability of where an electron may be found in those spots for each of those orbitals. The next type of orbitals of where we find electrons are what are referred to as d orbitals. D orbitals actually start on the n equals 3 level. That is where we first start to see d orbitals appear. Kind of like p orbitals, there's actually 5 different types of individual d orbitals. So there's 5 different types of individual d orbitals. That would mean if I max that out, how many electrons have I filled up all 5 of those? Yeah, 10 electrons max if we filled up. This would also be referred to as a subshell, right? Because we have a grouping of 5 individual orbitals that are all the same in the sense of d orbitals. So again, if we were kind of drawing our picture here, once again, on the first energy level, just the s orbital. On the second energy level, we have our s orbital. That is where we first start to see our p orbitals appear. And now we get to the third energy level where again, we still have our s orbital. We still have our p orbital. And this is our first appearance of d orbitals. Once again, that also being a subshell, a 3D subshell here, which is the one that could hold, again, a maximum of 10 electrons if you filled up all the individual d orbitals. But once again here, each individual orbital of those d's could only hold 2 electrons, yeah? Any questions on that there? You can see here that the d orbitals basically looks like 2 p orbitals kind of put together and one. And again, each of those lobes are the place where you would predict or probability of finding an electron. And once again, kind of in the middle where they all kind of come together. Again, you can kind of visualize where sort of the nucleus of the atom would be located. And here's what they kind of look like.
Y squared orbital has a cloverleaf shape that lies in the xy plane and is aligned along the x and y axes.
The 3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes.
The 3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes. The 3dyz orbital has a cloverleaf shape that lies in the yz plane and bisects the y and
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z axis.
So again, each of these shapes are really defined on what's known as wave function, and they're really all sort of probability maps based on calculations and mathematical theoretical type calculations. would you see these exact shapes? Probably not. But again, these are more like theoretical sort of mathematical predictions of where you would find these electrons in. The last type of orbitals that we come across that we deal with, I won't say really the last ones, but really the last ones that we do deal with are f orbitals. And they don't really start to appear until we get to the fourth energy level. So on the fourth energy level, that is where we first start to see f orbitals appear. They actually only appear on the fourth and fifth energy level, pretty much we use for the most part. They can go past that. For the most part, we only come across them in the fourth and fifth energy level. And the d orbitals, by the way, usually will max out for our purposes at like the sixth energy level is where they sort of max out the d orbitals. Unlike those, there's actually 7 different types of f orbitals. And if we have 7 different types of f orbitals, each could hold 2. We are going to max out at 14 electrons if we filled up the entire subshell. So once again, on our picture, n equals 1, our 1s, n equals 2, our 2s, 2p, n equals 3, 3s, 3p, 3d. I'm going to go up here just for space purposes. N equals 4. We have our 4s, our 4p, our 4d. Maybe I should went higher, further to the left. 1, 2, 3, 4, 5, 6, 7. We'll do that. 4f. Break between those two as we run out of room. So there we do end up where we first start to see really our f orbitals start to appear. And again, you can kind of see they look actually like 2 d orbitals kind of put together, most of them. And again, those are areas where we have high electron density and probability of. Yeah. It's a really bad 4 that somehow the letter part got lost there. Yeah, it should be 4. Yeah.
So I'm assuming that all these orbitals combined in order to figure out the best possibility of finding an electron then, or are they used separately?
Say it one more time. I'm sorry.
That all these different types of orbitals combined to find the best possibility of finding an electron, or are they used separately? Like from p orbitals to the s orbitals, and the d orbitals, are all used in conjunction with each other?
They are all used, but not used in a sense of they will all have electrons in them. So each element will have available to them, depending on their location and how many electrons there are and so forth, they will have available to them a certain amount of orbitals, if you will. They will be, as we'll talk about, they are filled sort of lowest energy level to highest. So basically, for example, energy is increasing as we go up this way, right? So as electrons basically go into the atom, they will always go sort of the lowest energy ones first, and then continue on until basically they fill up as many spots as they need. So that's why not all these orbitals, for example, will actually have electrons in them or contain electrons. They don't have to be filled completely all the way through. So when we talk about, for example, here, 14 electrons, 10 electrons, 6 electrons, and so forth, those are the maximum numbers of electrons if you needed to fill it up, right? So you could think of the orbitals like a room, right? And there's seats in there, right? There's like couches, chairs, whatever it is, right? And when you have people in the room, right, you may not need to use every seat, right, or every chair, but they're available to you if you needed to, or even like a dinner table or something like that. You got 6 seats around it or something like that. Maybe only 2 people come, right? You use 2 seats, but maybe have some family over and use all 6, right, if you needed to. And that's sort of the idea of how these sort of subshells and orbitals are. They're on a specific energy level. You have a certain number of orbitals available to you to use. You may not need to use them all, depending on what element you're talking about. Yeah. Other questions? So let's talk a little about the energy level of these guys. As we've seen, again, starting the lowest energy level, that principal quantum number of n equals 1, then we have our 1s, and then it starts to increase. And when we look at these different orbitals on the different energy levels, in the case of hydrogen, what we actually see is all the orbitals on a particular energy level are pretty much equal to each other. So this would be, for example, n equals 1, n equals 2, n equals 3, n equals 4. And obviously it continues on to 5, 6, 7, and so forth. But here we see that, for example, everybody on the second energy level is essentially equal in terms of energy. Everybody on the third energy level is also equal. By the way, what I just boxed, which is the n equals 2, this is also sometimes referred to as a shell or a level. Yeah. So a shell or level refers to basically all the orbitals that are present on that particular energy level. So the n equals 2 shell would tell you that we have a 2s and the 2p subshell present on that particular energy level. So, for example, if I wanted to know the maximum number of electrons in the n equals 2 shell, and I also want to know the maximum number of electrons in the 3d subshell, and I want to know the maximum number of electrons in a 4p orbital. So take a moment and figure out how many electrons, the maximum number of electrons on the n equals 2 would be. It would actually be 8 electrons. And the n equals 2 shell or level is all these orbitals that are basically on this one. And that would be 2 there, 3, 4, 5, 6, 7, and 8, right? So each one holding 2. So we could put 8. How about the number of electrons in a 3D subshell? 3D subshell would be, yeah, all these guys here, right? So all 5 of those, and that would be 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. How about a 4p orbital? So that is the trick question that sometimes is asked. A 4p orbital would not be 6 because what I just boxed is a 4p subshell, right? And that would be 6. A 4p orbital could be this orbital, could be that one, or it could be that one, but any individual orbital can only hold 2 electrons, yeah? Again, if we said 4p subshell, we would have 6 would be the correct answer in that case. First off, any questions on that there? Now, you probably don't want to draw these things if you wanted to figure out how many electrons, for example, were on a level or a shell, the entire energy level. So there's actually a formula if you want to know how many electrons are on a particular shell or level. You could use this formula. It's how many electrons or max electrons on a shell. That n is the principal quantum number. So that's the n equals 1, n equals 2. That's what the n is. Here again, you do want to actually square the number first and then multiply by 2. So how that works, for example, we just did this guy, and it's equal to 2. So we would have 2 squared times 2. So that is 4 times 2 is 8 electrons, right? If I did the third energy level, right? That would be 3 squared times 2. That's 9 times 2. That's 18 electrons. So let's see. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 18 electrons. Yeah, so if you filled up the entire shell, that's a good way to do that, especially get up to higher numbers like 5, 6, 7. You could just put it into that formula. And again, that tells you not necessarily how many are actually filled, but if you were to fill everybody on that energy level, how many you can put in there. Why does, say it again? Why does? They have more electrons because there is, technically speaking, f orbitals are where we stop because with f orbitals, it takes care of everybody on the periodic table. In theory and in math, it actually just continues on alphabetically after that. There's actually g orbitals and so forth. So there's more orbitals that go out and just goes alphabetical after f. So it's like f, g, and so forth. But mathematically, quantum number wise, there's actually more orbitals. We just don't use them because through like basically 5F takes care of everybody on the periodic table, basically, and stuff like that. But in theory, if you were to the math, which we were talking about, this is pretty much all based on math and calculus and probability sort of calculations. There's actually more orbitals available. We just don't really use them when we do things like electron configuration because we don't need them for what's up there. Yeah.
Five without 4 electrons, but they moved to 4. But when you wrote it out like that, where did they do the same? Because the little.
Yeah, so as I was just mentioning, in theory, for example, after when we get to the 5th energy level, and this would be something that you'll talk about in 1A, I think. But for example, if you went to the 5th energy level, there's actually what are known as 4 quantum numbers. We don't talk about all 4 of them here. You'll talk about 1A. But for example, when you have n can have values of 1 through 7. Okay. There's another quantum number which is known as L, and this is the angular quantum number. It basically tells you the type of orbitals that are available on an energy level. And L can have values of 0 to n-1, for example, okay? So what that means is, for example, when we get to our first energy level, that is n is equal to 1. When we do n-1, which would be 1 minus 1, the only possible value for L, which basically tells you the type of orbital that's there on that energy level, is 0. Right? When you take 1 minus 1, you get 0, basically. And a 0 represents an s orbital, right? So on that first energy level, that's why there's only an s orbital. Now, n equals 2, you can now have values for L of 0, because you could always have 0 on any energy level. But when I take 2 minus 1, I get what number? I get 1. Now, we just saw that the 0 represents an s orbital. When you get a value of 1, it represents a p orbital. So if we were to go up to like the 5th energy level, like you were talking about, n is equal to 5, we can have an L value that, again, will be 0. We also could have n minus 1, which is 5 minus 1, which is 4. And we could take whole numbers all the way up to 4 in that case. So we could have a 1, a 2, a 3, and a 4. So again, that is your S, that is your P, that is your D, that is your F, which pretty much will take care of everybody on the periodic table. But we also have another number based on the math of it, and that's what I was talking about, technically, G orbital, yeah? And what a G orbital could actually have in terms of how many orbitals a G subshell could have, you could go to M sub L, which is the 3rd quantum number, by the way. And what that is, it is values of minus L to 0 to negative L. And basically, for example, if we took that value that we got for the G, it could have values basically of minus 4, minus 1, I can learn to count, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, and plus 4. Now, each of those numbers actually represents an individual G orbital, yeah? And each of those numbers then represents one individual orbital that can hold how many electrons? 2, right? And if we count up the numbers as 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that's another 18 electrons. So that's why we were asking when you do the math, right? Where did all those electrons go? They would go theoretically into these orbitals here that we actually don't need for anybody on the periodic table, but that's where those would go. And by the way, that's why also when we do our P, right? We do our M sub L for P, that is minus 1, 0, and plus 1. That's how many numbers? That's 3 numbers, right? Each of these represents the px orbital, py orbital, and the pz orbital. So all these kind of orbitals are based on the quantum numbers, which they really should teach people first because that's really where all these orbitals come from. But they do teach you that in 1A. But they're based on these mathematical sort of theoretical calculations, and that's how we know when we get to those higher orbitals, even though we don't use them, again, they're available if we were needed. They would come up with a new element that had that many electrons that needed to go there. That's where they would go, stuff like that. Does that sort of make sense? And clear, we're not going to do any of the quantum numbers part, other than the n part. You need to know n equals 1, 2, 3, 4, 5, 7. Any questions on that? All right, we'll lay it up there.